MDM4U 1.7 problem solving with matrices. So we're going to learn how to multiply using matrices. We're going to start with multiplication by a scalar. Multiply each entry by the coefficient. So if A is defined as the following matrix, 3A is this scalar quantity 3 multiplied by each entry inside of the matrix. So 3 times 5 is 15. 3 times -1 is -3. 3 times 2 is 6, and so on. However, multiplication of matrices when they have different dimensions can be a little bit more challenging. Matrices can only be multiplied when the inner dimensions are the same value. So, we define matrices by the number of rows and then columns. So, if a matrix A has 5 rows and 4 columns, and matrix B has 4 rows and 1 column, we look at the inner dimensions as the columns of the first matrix and the rows of the second matrix. Notice that that's 4 and this is 4. So when they're the same value, matrix multiplication is allowed, and then the resultant matrix, meaning the product when we multiply two matrices, will be the outer dimensions, 5 times 1, or 5 by 1. Okay, so multiply each row of the first matrix with each column of the second matrix to get the resultant matrix. So we'll follow the following visual here. This is just in general with letters, but what we're doing is taking a look at the first row and multiplying it by the first column. And each of the entries are paired up with multiplication and then added together. So we have A and E multiplied plus B times G, as you see here in this position. Let's first note that this has 2 rows and 2 columns vertically. Same thing here. We have 2 rows side to side and columns too. So the inner dimensions are the same, which allows for matrix multiplication, and the outer dimensions give us a 2 by 2 matrix. So we're going to continue. Our first step was take the first row and multiply it by the first column. This was done here. Our next step is to multiply the first row times the second column of the second matrix. So let's look at those values. A times F plus B times H. And notice that this is row 1 and column 2 of this matrix. So that produces the entry in row 1, column 2 in the resultant matrix. Next, we've distributed this through both columns. Next, we're going to distribute the second row through each column of the second matrix. So row 2 multiplied by column 1. C times E plus D times G in this space. Next, second row, second column. C times F plus D times H. Now let's try this with an actual example. And by actual example, I mean that the matrices have values for the entries. So starting off, we're going to have our first row times the first column, which will be 1 times 5 plus 2 times 7. And we can show this intermediate step when solving with actual values, or we can just enter these values into a calculator and write the result. So we know that it's a 2 by 2 and a 2 by 2 matrix. Matrix multiplication is possible because the inner dimensions are the same, and the outer dimensions tell us that we will have a 2 by 2 matrix. So our next entry of our resultant matrix will be made up of our first row times the second column. 1 times 6 plus 2 times 8, which is 6 plus 16, which is 22. We're into the second row of the first matrix now, times the first column. 3 times 5 plus 4 times 7. and then first row times the second column. So that will be 3 times 6 plus 4 times 8, which is 50. So you can copy these next examples using the same strategy. First row times the first column, and then first row times the second column. Second row times the first column, and then second row times the second column. Notice that this is 2 rows by 3 columns, and the result will be, with the inner dimensions being equal, matrix multiplication is possible, and the outer dimensions tell us that we'll have a 2 by 2 matrix as our result. So try this example on your own. Use this as a template for multiplication, and we would have, we'll do each example, 2 times 10 plus 3 times -4, -1 times 6. Then we have the first row times the second column, 2 times -2 plus 3 times 3 plus -1 times 2. And then our second row multiplied by the first column, -4 times 10 plus 5 times -4 and 0 times 6. Then we're into our last entry. We have our second row multiplied by the second column. -4 times -2 plus 5 times 3 plus 0 times 2. And this is our result. So we're going to talk about a couple of special cases here. We have the identity matrix. So the identity matrix, think of it as the number 1. It behaves in many ways like the numerical value 1 in mathematics, except that it is in matrix form. A matrix that is an identity matrix, denoted I subscript n, if it is a square matrix with dimensions n by n, it has 1 in each entry on the diagonal, as you see here, going down to the right, and it has 0 in every other entry. Good. So it has the property that if you take a matrix and multiply it by the identity matrix, notice that this I to the n is an n by n matrix, so this would be a compatible multiplication. And the product would be then m by n, the outer dimensions. So taking a look at this example, when you do matrix multiplication, our result is that initial matrix. So it behaves like 1 in that sense. For example, 1 times 10 is 10. And the purpose of this matrix is we have applications in linear algebra, and we can use row operations that are similar to the elimination method that we've learned with linear systems. But this can solve with many more variables. So it becomes a powerful tool, very helpful to have in advance to university. Next, the inverse matrix. I'm going to first state that this is a formula or technique that applies specifically to a 2 by 2 matrix. So therefore, if A is defined as A, B, C, D, then A inverse is equal to the following. This value up front is called the determinant, and it's evaluated as 1 over A times D minus B times C. And then the matrix entries are moved. So A and D switch, and then B and C are negated. So A inverse has the property that A times A inverse, or A inverse times A, is equal to the identity matrix. So this example, A is equal to 1, 2, 3, 4. Then find A inverse. So what we're going to do is substitute into our equation and evaluate. So you can check to see, and you can use this as an example, that A times A inverse is in fact equal to the identity matrix. So, encoding and decoding messages using matrices. During the 1930s, Lester Hill, an American mathematician, developed methods to encode and decode messages. This is a simplified version. but this is a great example for instructional purposes. Develop an encoding strategy. So this is a little bit too straightforward. If A was 1, B is 2, C is 3, all the way up to Z is 26. This could be rearranged in any way to make it further complicated. The message is, as provided by the text. Step 2, determine your message. Dog ate my homework. Part-time comedians writing these textbooks. Step 3, encode using our alphanumeric strategy. So let's take a look at how this is being encoded. 4 is D, 15 is O, 7 is G, and 1 is A. So it's a 2x2 matrix reading left to right just like a book, and this is how the message will be sent. Now, to make it one step more complicated, let's say that someone had your encoding strategy, then they would just be able to decipher this message and there would be problems, potentially. So, to make it one step further, a coding matrix could be used. And the most basic matrix you can think of, 1, 2, 3, 4 is what we will use. And if you take that C matrix, multiply it by each of those steps in our encoding matrix. So this is 4, 15, 7, 1, as you see here, multiplied by C, and we get a different value here. This will be our message that we would send that would be nearly impossible to decipher if you were to send that to someone. It'd be very challenging. Create the decoding matrix. Now, C inverse is calculated using the formula that was provided. And when you have this inverse matrix, what you can do is multiply that by each and every single one of those encoded messages to get the original message. It undoes it, just like inverse operations. So then we have our message, and if we use our decoding decoding strategy, it says dog ate my homework. Very important that no one's privy to this information. So good luck on the homework questions.